Hello everyone, welcome to the Differential Geometry and Physics seminar. Today we're very happy to have Andrés Franco Valiente talk about tropical, topological, tropological sigma models. Andrés, please.
Thank you, Max. So yeah, sorry for the kind of a tongue twister title. Over here, the main thing that I'm going to introduce is something that we're calling the tropical topological sigma model. But as we were developing this, we kept saying the word tropical and topological so often that it kind of ended up accidentally becoming tropological. So if you want to search any of this stuff, you Google tropological sigma models, and it should pop up. And so this is a work that we've done with Emil Albrychiewicz, Kai Isaac Essler, and Peter Hořava, I think a few years ago. There's been a few follow-ups since then, and a lot of unreleased work, but I'm going to try to give a sort of overview as to what these sigma models are. I know that my general feeling is that some of the audience is going to be more mathematical, and they may not necessarily know too much quantum field theory, so I will give a rough schematic introduction as to what I mean by quantum field theory, at least in this context. And then we're just going to review the standard things and see what the new results are. So let's get started. So, go. Okay, so I want to get started with the physical motivation. One of the things, the reason why we're constructing these things is because we're actually interested in string theory. And the way in which I'm going to view string theory in this case is I'm going to view it formally as an integration theory of maps, where you have a map from some sort of Riemann surface that we call the world sheet and some sort of target space manifold that I'm going to call M equipped with a Riemannian metric G. In reality, it's actually a lot more complicated than this. We consider 4 more complicated maps, but as a good first order approximation or zero order approximation, this is how we should be viewing it. So historically, if you haven't been exposed to string theory, we kind of view it as a machine that connects a whole bunch of different areas of like mathematics and physics. You might have heard in the mathematical literature that we have things like scattering amplitudes, trying to reduce these amplitudes into like smaller computable parts, results from 2D conformal field theory, vertex operated algebras, the stuff that you see in topological field theories and so forth. They kind of more or less all arise from string theory. Things like dualities, mirror symmetry, all that's nice brain and category theory stuff. There's many different ways in which you could actually connect it just by doing calculations and string theory. And essentially, when you go through all these things, you start to realize that there's a lot of assumptions built into string theory. From a physics point of view, most of these results are based off something that's known as thermal equilibrium. And the useful thing about this is that it allows physicists to construct these things that we call Hilbert spaces of asymptotic states. Now, the thing that's important about this is that this lets us construct interesting objects like scattering amplitudes. And from the scattering amplitudes, that's generically where you can start, coming up with all these things like conformal field theory, brains, mirror symmetry. It really comes from that original construction. So if you break that physical assumption, you allow the so-called target space geometry to be far from equilibrium, then there's actually there's generically no accepted notion of asymptotic states. So suddenly you're based with this question of like, what do you calculate? How do you make progress? How do we turn these into actually rigorous mathematical questions that actually make sense? So it turns out that part of the answer is given to us by non-equilibrium physics. It's based off something known as the Schur-Kelch formalism. You don't have to know quantum mechanics. The important thing is that quantum mechanics tells us that if you want to take whatever physical model out of equilibrium, what you do is you kind of double the maps. You're going to end up having a map that is somehow propagating or evolving forward in time with respect to some time function. There's going to be a map that's propagating backwards in time with respect to that time function. And then they're kind of glued around at this turnaround point that we call T wedge. So that's the important thing. We take this result from physics, and then we try to apply it from string theory. And it turns out a few years ago that Hořava and his student Christopher Magni were able to actually show that this results in a refinement of string theory. You actually end up getting a world sheet, which you remember was the source a source space. It ends up getting this sort of refinement where you have a triple decomposition where there's part of the world sheet that's actually going forward in time, there's part of the world sheet that's going backwards in time, and you have this sort of glued wedge region. But the interesting thing about this wedge region is that even though it's topologically a two-dimensional manifold, from the point of view of like the metric tensor and the complex structures and all the other geometric data on the world sheet, it's actually one-dimensional. It sort of collapses in on itself. And the question that we were facing is, well, how do you construct this wedge region explicitly? So we were looking like, how if all this stuff is kind of based off relativity, or we're treating all the dimensions the same, is there any way in which you can construct an anastrophic limit? And so, you search through all the physics literature, and you find out that there are actually methods in order to do this that are not just things like dimensional reduction. It turns out that there's these things in M theory called PQ string networks that actually show a similar collapse. And when you go through all those calculations, it turns out that there's a very close connection to tropical geometry. So that was the big hint. The big hint is that if we want to construct this wedge region explicitly, we have to somehow leverage tropical geometry and try to see how do we create a sort of tropicalized string theory. And there was another hint from mathematics literature, specifically in algebraic geometry, by this mathematician called Mikhalkin. And Mikhalkin essentially said that if you want to compute the Gromov-Witten invariance of some sort of symplectic geometry, instead what you can do is you can look at the so-called tropical limit of that symplectic geometry, and it should be able to give you the same calculation. And so we're going to use that as a check in order to actually construct these field theories. And so, there is a mathematical motivation behind
Andres,
this.
can you
Yes.
quickly say what the PQ are in your PQ strings in M theory? PQs, yeah.
Yeah, so these PQ string networks, essentially, they're composed out of well, when you go through all you go through all the calculations of string theory, it will turn out that there are many different kinds of strings that one can consider, and they are classified by these things that are known as electric and magnetic charges. And so that's what these PQ numbers are. And mathematically, I believe that they are some values in some K theory class.
I'm
And
asking, I'm asking because M theory doesn't have any strings, right? It's like I know of PQ strings in
oh,
type 2B, but
yeah. Sorry. So that's another technical detail. So M theory itself doesn't have any strings. You're right that it has these M branes. But when you actually when you take a particular dimensional reduction limit to reduce it down to type 2A, you end up with these sort of piecewise linear strings that are connected. So this comes after the dimensional reduction. Yeah.
okay, thanks.
Yeah. And so, the mathematical motivations, there's an infinite number of them actually, because a lot of these statements are, in some sense, you can't make them too rigorous. So, as mathematicians, we'd like to be able to really know what we mean by all these things. The one that I'm going to try to emphasize for this particular seminar is that we would like to construct the notion of tropicalized functional integration. And so we already know that if you take this particular quantum field theory that's known as the type A topological sigma model, you can actually compute the Gromov-Witten invariance. And the question is, if Mikhalkin's theorem tells us that the Gromov-Witten invariance can be computed by taking the tropical limit on the mathematical side, then how do you directly take that tropical limit when we're considering the A models of quantum field theory? The theorem exists and it tells us that it should work, but we don't really know how to do it from the path integral point of view. So we're left with the immediate question of do we have to reconstruct the whole framework of functional integration? What does that even mean? Do we have to do it in terms of the tropical semifield? These sort of questions. So before we actually get into that, we kind of we want to mention that tropical geometry has actually appeared in a whole bunch of different places before. It's not just us exploring and be like, oh, tropical geometry. We actually had actually another speaker about a month ago. I think it was Baranski from Perimeter, and he was talking about how do you have a tropicalized quantum filter, and then he had these amazing results where instead of calculating for 2 loops, you can calculate things up to 50 loops. Tourcoing is also someone who talked about tropical limits of string amplitudes. And Nima Arakni Hamad has been pushing on tropical geometry as a method to simplify scattering amplitudes and so forth. And of course, we have, Eberhard and Sebastian Mazera, that we're actually showing that tropicalization happens when you have these world-sheet unitary cuts. And that was actually a big hint and sort of pushing towards this direction. And this list is not exhaustive. People have been examining tropical geometry from both the physics and the math side. There's a whole bunch of papers that are coming out now. So let's just start basic. Let's kind of get an idea of what is functional integration at a very pedestrian level, so that way we don't really lose anybody. So the way in which we should think of functional integration can actually come from basic probability theory. What I'm going to call a zero-dimensional quantum field theory, and I'm going to call it a QFT with lowercase, with a single random variable, is essentially when you take that single random variable and you integrate over all its possible realizations. And so over here, this S of X is what we're going to call the Euclidean action. It generically is a polynomial. It can be more complicated than this, but for our purposes, we're going to treat it as a polynomial. the important thing to know is that generically we care that we have this A2 term, and this A2 term, this quadratic looking term, is going to essentially be the Gaussian part of this zero-dimensional quantum filter, and that's going to let us compute essentially what we call correlation functions or observables. And so that's defined in a natural way. You would put in some sort of moment that I denoted as x kappa, where kappa is an integer. And then, you can easily generalize this to a zero-dimensional quantum filter with n random variables, where you instead of integrating over a single random variable, you would integrate over n, capital N, different random variables, and then the corresponding observables will be defined analogously. And so you might ask, okay, great. That I'm not sure how that's quantum field theory yet. This is just basic probability theory. You can take, if you look at this, if you look at the structure of the n-dimensional case, then you can kind of imagine that you can push this analogy to the continuum case in infinite dimensions by making the formal replacement where these xi's end up becoming x of t's, where t is now the index label. And so t is a continuous label that goes from 0 to t in some interval. And so really you have an infinite number of indices there. And if you do that, then roughly you can say that this defines what we're going to call a one-dimensional quantum filter with an effectively infinite number of random variables. But, to say you have an infinite number of random variables, that kind of loses its meaning. So physicists would say we have one field, one quantum field, and that quantum field would be that entire path x of t. And so now, if you take that, if you look at what the Euclidean action looks like, you would have this sort of non-local A term, but it turns out that this is uncontrollable and unphysical for a lot of purposes. So generically, physicists are actually motivated in the case where this A of t is a local operator. So we insert a Dirac distribution in there, and that collapses the integral to a single integral. The sort of differential operators that really come in practice generically are differential operators that you would see in geometric analysis, things like Laplacians, the Dirac operator, and other more complicated versions of these things. And so, the way in which physicists treat it is essentially that you can do calculus with it. You can take this as a formal expression. It's not rigorously defined. We have no clue what it means in a lot of cases. And if you do calculus with it, you can end up getting a lot of interesting results. You get connections to heat kernels and other sorts of geometric objects. And one dimension, it turns out that these one-dimensional quantum filters can be made rigorous to some degree when the corresponding Euclidean action is simple. And people have developed these things. We have things like Wiener measures, rough paths theories that you may have heard about, and stochastic geometric analysis when you're not just dealing with a target space that's Euclidean space. But there's really no common method to understand quantum filter above 2 dimensions. And so what do I mean by above 2 dimensions? I mean, like, if instead I was saying I want to integrate over maps that go from some 3-dimensional manifold M to some, and it's real value, so a map from M to R. We don't really know what it means to integrate over those maps. And of course, you can consider a lot more complicated objects like vector fields, connection spinor fields. How do you integrate over all spinor fields? Like, what does that even mean? That's what I mean by it's kind of not made rigorous yet. The real part where it starts becoming an issue is when you really look at the analysis. So for now, you should really just treat it as a sort of a formal analog. And what we're going to try to do from the mathematics side is we're going to take the sort of cartoon physics picture and we're going to reduce it down to finite dimensions where we can actually make it as rigorous as we possibly can. So for the purposes of this talk, you should view quantum field theory now with capital QFT, so the whole field of study. You should view it as the calculus of these functional integrals. That's one perspective. Not all physicists will agree with me, but that is one perspective that you can take in order to just kind of proceed and see where you want to go. Okay, so now tropical geometry, right? So it turns out the tropical geometry that we're going to have to use is actually very introductory. You don't have to know a whole bunch of algebraic geometry, but of course, the further developments would require it. So the thing about tropical geometry is that you can define their addition and their multiplication between tropical numbers as a sort of deformation of the standard addition and multiplication of actually it should be the complex numbers, not the reals here. And so it's going to be defined in such a way that when you multiply two tropical numbers, it becomes the addition. And when you add two tropical numbers, it actually becomes the maximum operation. And this, when you take this sort of deformation limit with the h bar, this is really known as the Litaunov-Maslov dequantization. And we're going to use this throughout the paper. We're going to see that this is actually the key tool that allows you to so-called tropicalize quantum field theory in this context. And so generically from mathematics side, what you can do is you can look at a complex manifold M, for example. You can equip it with local complex coordinates, and then what this log map essentially is going to end up doing is, because it takes a modulus of all the complex coordinates, you actually forget the phase. And what you can show is that as you take that limit as h bar goes to 0, with respect to some topology and some convergence and so forth, some convergence criterion, you can actually show that these complex manifolds actually converge to piecewise linear structures that are described by real algebraic geometry. And so that's where the tropical geometry comes in. And so the interesting thing that I will let you know is that there's two perspectives that we ended up using in this paper. So over here, if you look at complex projective space as an example, so CP1, if you want to tropicalize that, then a tropical geometer might actually end up saying, okay, great, you can do that. If you want to consider TP1, the tropicalized projective space, then you would end up with this sort of interval after you tropicalize it. And the two coordinate systems would, one would include the minus infinity and the other one include the positive infinity. Sorry, that's a typo on figure B. Instead, what we're going to see is that you can actually blow up this picture and retain the theta angle. And so you can view the tropicalization as still being, topologically an S2 with those two punctures, but you're instead going to have a foliated manifold. And these foliations, only when you quotient them out, you can recover the tropical geometry. So there are two ways of viewing the same thing. And we're going to see that this foliated manifold picture that we call the covering space perspective, it's going to end up being very useful in order to actually define these path intervals. Okay, so to review what the quantum field
Sorry, quick question.
is. Yes.
Andres, was this particular to the example, or is this going to be a generic feature of tropicalization?
Oh, this will be a generic feature of when we do it. Yeah. This is just I just wrote down an example here for CP1, but it can be extended to, I think, effectively any piecewise linear structure. And what you end up getting in general is a Riemann surface that has foliations, but the foliations can possibly be singular at the juncture points.
I see. So, okay, thank you.
Cool. Okay, so the type A topological sigma model, if you haven't seen it before, you should just think of it for now formally as an integration theory of maps, which we also call fields, from a Riemann surface to a target space. The A model does come equipped with a nilpotent Grassmann odd differential operator on the space of fields that is known as the BRST differential. We're going to know that Q. And generically, we restrict to symplectic geometry target spaces. So we have target space manifold M. It's going to be equipped with some symplectic structure omega and some complex structure J. And, all the usual compatibility conditions. So generically, when we say the type A topological sigma model, we're really thinking about a quantum field theory of pseudo-holomorphic maps. And when you go through all the calculus of these functional integrals, it's known that the so-called correlation functions, they generically only depend on the target space symplectic form. And so how do you actually compute that from the functional integral perspective? It actually really depends on that BRC differential. It's important that it's nilpotent because then we can actually formally understand it in terms of equivariant cohomology. In fact, this part could be made quite rigorous, but we won't get into that in this particular talk. And so, the way in which we define the BRC differential in practice is that if you have some sort of topological invariance of a particular map, so the map here we're going to denote as phi I, then if that topological invariance is generated by a vector field epsilon I, then the standard procedure is actually to replace that vector field epsilon I with a Grassmann odd vector field Ci, which we call the ghost field. One thing. When I write these indices, I don't mean that it's the component of the vector field. I'm using this convention known as the Penrose abstract notation. So it's really just a placeholder symbol to denote that this is what sort of tensor structure it has. So noting that it's a vector, but I'm not literally writing the components. You can still treat these as exactly how you would treat them in differential geometry. Okay. So if you have this BRC differential, which we can understand as the equivariant differential, then the localization of the functional integral should then proceed by the fixed points of the BRC differential. So this would be very close to the Berlin-Berg localization or the Duster-Matt. And so in finite dimensions, we can actually see this a lot more explicitly. So as a finite dimensional analogy, you can consider the case when you have a manifold M that we're going to integrate over. And if that's a compact manifold and there's a G action for some sort of compact Lie group, again, generated by some vector field B, then you can formulate equivariant cohomology in terms of this thing known as the Cartan model. the equivariant differential is then defined by this sort of shifted exterior derivative minus an interior product along the vector field that generates the g action. The important thing is that this equivariant differential is actually nilpotent, so it lets you define new equivariant homologies. So in terms of calculation, what you can do is you can take an equivariantly closed form. So in other words, it's close under the G equivariant differential, and you can ask, how do you compute this integral? And what you can do is you can actually deform it by an equivariant exact deformation. So over here, I'm multiplying by this exponential of some term that is dg exact. And then you consider this new integral z of t. And notice this is a finite dimensional integral. This is no crazy functional integral. If you do that, then you through a short calculation, you can actually show that it's independent of t. So if you look at the form right here, right? Look at equation 13. Does it have any t dependency? 14, when I conjugate it, well, not really conjugate, but when I deform it, I have this t dependency. You take a simple derivative, and then after some Stokes theorems, you can show that it's t independent. And so the key thing is that allows you to actually compute this partition or this integral by taking either asymptotic limits. You can take the 0 limit where we recover the original integral that we care about, or you can take the infinite t limit. And it turns out that if you go through, any of these standard books, for example, like BGB or the heat kernel and asymptotics book, the rack operators book, then what you can really show is that when you take the t goes to infinity limit, you really get a sum of fixed points of the equivariant differential, and the result is actually a sum over essentially the equivariant Euler class of the directions that are transverse to the fixed points of the equivariant differential, and so that's what we're calling the fixed point lotus. So this is all, you can make this completely rigorous. You can go through all those arguments. What we're going to do is we're going to take this as granted and try to apply to the functional integral. And what that's going to do is it's going to reduce the infinite dimensional functional integral into a finite dimensional one. And so what we really mean, what physicists mean by infinite dimensional localization, or in the literature as it appears as supersymmetric localization, what we're really saying is, okay, take a schematic functional integral where we're integrating over some particular prescribed space of fields, and then what we're going to do is we're going to deform this by no longer equivariant differential exact form, but a BRST exact term. And then we're going to look at the fixed points of the BRST and try to reduce it down to something that's actually in finite dimensions that we can actually make rigorous. And so the only thing that you have to know from the previous literature is that the correlation functions in a topological field theory, which is a special kind of quantum field theory, they're usually going to correspond to topological invariants of the target space. And in particular, for the standard A model, the results of those correlation functions will be the Gromov-Witten invariants. And so what we want to see is, if you take the A model, and then you decide to say, well, how do you take a tropical limit of this path integral? What happens to the Gromov-Witten invariants? Do you still get the same invariants as suggested by Mikhalkin's theorem? And what we're going to see is that you actually get them precisely on the dot. And so if you look at the fixed points of the BRC differential, then, if you equip the fields with local complex, if you equip the source space and the target space with local complex coordinates, then you can write the fields in terms of these objects. So phi I here, and I didn't actually know what they are because it's not important for us to talk, but the important thing is that phi I here is the map that goes from sigma to m. And over here, psi I is going to be a Grassmann odd vector field that also goes from sigma to m. But these are the things that we called ghosts that we introduced in the previous slides. What you can show is that the BRC transformation laws take the form of these equations 18 to 21. And if you ask what are the fixed points of these BRC transformation laws, then what you're going to end up getting is you're going to localize onto the space of essentially constant maps. But they're not entirely constant maps, actually. No, sorry, they're not constant maps. Over here, notice that we have phi bar and phi I. So you're going to get some maps that are going to be holomorphic and some other maps that are going to be anti-holomorphic. And then the Grassmann odd vector fields, those guys are going to vanish. So if we look at the path integral in that limit, then we should end up getting something interesting. And so we're going to apply that to the A model. Now, when the target space manifold is just a one complex dimensional manifold. And so we're going to choose target space coordinates capital Z and Z bar. If you rewrite the localization equations for the previous slides, then it really is just looking like the Cauchy-Riemann equations. You get this partial bar of Z. And then the Maslov dequantization limit of this equation, you can essentially write it in polar coordinates. And when you write it in polar coordinates, you actually get this interesting form, which is equation 26, where essentially you can plug that deformation exactly into the localization equations as it is, and then take the limit as h bar goes to 0. Now, the thing about this massive dequantization is that before you apply it to the localization equations, you actually find out if you want this operation to be associative, it will require you to accept that these coordinates are actually multi-valued. And so you might end up trying to kill the project at this point, because you might say, well, does that mean we need some sort of weird multi-valued functional integral? Can we make sense out of this? And it turns out that you can get away with it as long as, you can get away with constructing a single valued functional integral as long as you introduce an additional gauge symmetry. And we're going to see that gauge symmetry pop out after we take the limit. And so we're also going to deform the target space local coordinates. So in the previous slides, so that everyone's clear, in 26, we're going to do a massive dequantization of the world sheet complex coordinates. So there's little z, little r, and little theta. And we're also going to deform the target space complex coordinates. That's going to be x and capital theta. Okay, we're going to do that deformation simultaneously on the world sheet and the target space. When you do that, then the localization equation takes this form. And what you can do is you can formally separate this out into the real and imaginary parts. And if you just formally take the limit for a moment, without worrying about any issues of convergence or with respect to what topology, then you're going to end up getting these equations 29, which essentially is a tropicalized version of the Cauchy-Riemann equations. What we want to do now is we want to take equation 29 as our starting point. We want to say, does this equation make sense? And if the local solutions and also the global solutions to this equation, if they make sense, can we construct a cohomological filter about these localization equations? And it turns out that you can do precisely just that. And so how do you check, if the global solutions work? You can solve them directly. If you solve it on the sleeve, so that means a cylinder across an interval. So no, literally a cylinder, sorry. So an interval across a circle. Then what you're going to actually find out is that the solutions are going to precisely be a zero mode that we're going to call x naught, so just a constant number. But you're going to get this additional winding number n. And here's an integer. And so at first, it doesn't look like it's piecewise linear. But what you can do is you can actually glue the solutions across many different sleeves. When you do the calculation carefully and you put in all the boundary conditions, what you find out is you actually get piecewise linear functions. So interestingly enough, right, what ended up happening is we took this localization equation. We just said, okay, great, we have this localization equation. We know it should give us something tropical by all these other arguments. When you go and solve those set of PDEs, you precisely get these tropical curves, because the definition of a tropical curve is that precisely you're getting a piecewise linear structure. And so the amazing thing about that is that we know that these tropical manifolds, since they're only really exhibiting discrete symmetries, we know that the only way in which you can relate these tropical coordinates to each other is actually by having general matrices that are integer valued. And what you can check is that if you try to construct any interesting interaction terms for the corresponding quantum field theory, you can't do it. So as a result, all these tropicalized topological field theories that we have seen thus far, they're generically going to be free field theories. And the thing that's very useful about that is that in terms of calculations, that means that they get reduced down to Gaussians, and we can definitely compute Gaussians. And so that's the wonderful thing about this. And so if you want to take that limit and kind of not do it in a particular coordinate system, then what you can do is you can rewrite everything in a covariant form, covariant on the world sheet anyhow. And what you find out is that since we know that the localization equations of the topological A model are really just pseudo-holomorphic curves that depend on two complex structure that we're going to call epsilon hat and j hat, you can check that if you take the tropical limit, they're no longer complex form. They're no longer complex structures. They actually become nilpotent endomorphisms of their respective tangent spaces. So now they satisfy this epsilon squared is equal to 0 and j squared is equal to 0. And since these are a different object, we're going to call these actually Jordan structures. Jordan because it looks like they have Jordan block structure when you actually put them in the adapted coordinates, which is the polar coordinates that we had defined before. Interestingly enough, I think there was another seminar a few weeks ago where there was another mathematician whose name I'm unfortunately forgetting right now, who was also looking at singular algebraic varieties. And interestingly enough, they also found some nilpotent endomorphism, and they also called it a Jordan structure. And I thought that was actually really cool. It looks like these sort of things are just naturally popping up in a whole bunch of different areas when you're taking these sort of singular limits. Okay, on continuing onwards. And so if you look at the tropical limit of these equations, is formally all you have to do is you replace the complex structure with the Jordan structures. And you can check that if you put it back into the elliptic coordinates, you're going to recover exactly the localization equations that we had originally obtained. And so the interesting thing about it is that compared to the relativistic case, and by the way, just to be clear, the relativistic case means the original sigma model. When we take the tropical limit is somehow treating the directions differently. So the theta direction is different from the radial direction. So we say that's a non-relativistic case. So in the relativistic case, the worldsheet complex structure actually gives us a direct sum. And in the non-relativistic case, because we actually have this nilpotency condition, we actually get a natural two-step filtration. We actually have a flag structure. And so because we're dealing with one complex dimensional worldsheet essentially, but it's not really complex dimensional because we don't have a complex structure anymore. If you're dealing with two real dimensional worldsheet, then that filtration that you have that's given by the Jordan structure actually automatically induces an integrable distribution of the tangent model. So what that means is that we can actually construct a foliation, and that's where the foliations are coming from. You're able to do this directly for radius theorem as long as you stay away from singular points. And so we should expect to actually find singular points because if you have ever done any calculations in tropical geometry, we always have these sort of juncture points. And at that juncture point between, for example, like 3 incoming branches, what you're going to end up seeing is that that's where the foliation is going to develop a singularity. And so those points have to be treated separately. And in the paper, we do an analysis of saying that you can actually treat it consistently, but we're going to leave that for details. I think it's worth noting here that this is what happens because the worldsheet is too real dimensional, and the target space is also going to be too real dimensional in the simplest case. But if you extend this to target spaces that are higher than 2 dimensions, then we already have some sort of preliminary results that you don't get a foliated manifold on the target space, but you actually get something that's a bit more general. You actually get a filtered manifold. And so I think this is actually something that's interesting because now you might ask the question, are there any sort of natural invariants that a filter manifold would have? And can these topological sigma models somehow probe them? And so we did not follow up on that, but it would be interesting to see if there are such invariants. And so the interesting thing is that, if you remember the standard topological sigma model, the key player is really the complex structure. And you might ask, are there natural symmetries that the complex structure comes with? And it turns out that now in our case, when we have a Jordan structure, there are new symmetries that actually come out. They turn out to actually only act along one direction if you look at the way in which we deform R. And the theta direction does get shifted, but it's only getting shifted by a linear power in theta. So this is some kind of new shift symmetry that we actually haven't seen before. The parameters are actually projectable functions. I am not sure at the moment if it has some relation to some of the things some of you may see in the condensed matter literature, things called subsystem symmetries. It seems as though there's a rough relationship, but we haven't actually said anything about that yet. Okay, but moving on, another important observation is that if you take the tropical limit of the worldsheet metric and its inverse, then they're no longer going to be inverses of each other. Instead, to satisfy this mutual invisibility condition, and it turns out that you can, if you look at how you can preserve that equation, then you can actually perform a conformal rescaling of G and H with opposite conformal weights. So if one goes with E omega, then the other one will go with E to the minus omega. And it turns out that if you look at the Lie algebra of that symmetries, it's going to recover the symmetries of the Jordan structure. So you actually have 2 ways of viewing the topological sigma model. You can either view it as a theory of 2 degenerate metrics that satisfy this simultaneous conformal rescaling, or you can just deal with the Jordan structure and ask, can I treat it as a theory of a topological Jordan structure and its symmetries? And that will be important later because if you want to make a theory where you're actually integrating over the Jordan structure, so in other words, a theory of dynamical foliations, then it matters whether you're going to use the metrics or the Jordan structures. This is a natural question to consider if you're going to, for example, say, if I have a standard topological sigma model, how do I couple that to topological gravity? In that case, you want a theory of dynamical metrics, but whenever you look at the correlation functions, you better make sure that the correlation functions are somehow independent of that metric that is dynamical. And so we're gonna revisit that later. The interesting thing is that the localization equations actually also have an additional symmetry. You can find out that they have this additional symmetry that we're going to call the alpha symmetry that we're going to use later in order to pretty much show you how to extend the construction from a sleeve, so just the S1 constant interval, to a general Riemann surface. And so if you want to formulate the theory on higher genus, like I said, you have to consider these higher singular foliations. And the key trick is essentially to define new local coordinates so that you can actually naturally extend these localization equations. But what you actually end up finding is, if you remember what the solutions look like, you had this extra integer winding number. And so when you actually extend the solutions, what you're going to actually end up finding is that they satisfy a condition between all of these winding modes, right? So all the, if you look at this example in the figure, if you have winding modes that are coming from the top, bottom, right, and left, then what you're going to see is that they all have to actually add up to 0. But if you know a little bit of tropical geometry, then you've seen this equation before. This is actually the balancing equation that you get at a vertex, and so it's reproducing the same structures. So that was actually a relatively nice finding, that it's somehow consistent with the results we know from tropical geometry. But now moving on to actually build the action. Is there an action for this theory? How do we relate this back to functional integrals? And so it turns out that there's a very natural construction that you could do using BRST cohomology. And so, as I said earlier, we're going to introduce a pair of Grassmann odd vector fields known as ghost fields. We're going to do them as psi and capital psi. They come with a gradient that's known as the ghost number degree, and we assign ghost number 1 to both psi and this both face psi. And then we can actually group these fields into components of a field multiplet that transform under the BRST symmetry. We call those BRST multiplets. And so in the adapted coordinates, under the action of the BRST differential, it's going to take the target space coordinate x, and it's going to transform it into the ghost psi. And we want this BRST differential to be nilpotent, so you naturally actually end up defining that the BRST differential on psi is equal to 0. Over here, you have to keep into account that we are using commutators when the fields are Grassmann even, and we're using anti-commutators when the fields are Grassmann odd. But you can write this in more general notation where you just use a super commutator. But in any case, in order to proceed with the construction, you need to remember that the action is actually a grade 0 object. So you actually need to introduce something that has minus grading. And this new BRST multiplet, where one of the fields chi has ghost number -1, and the auxiliary field number auxiliary field B has ghost number 0, they, under the BRST differential, they actually satisfy this relation. But the interesting thing now is that you can actually write a BRST cohomology representative for the action by literally just taking all the ghost degree 0 terms that you can come up with that actually contract in a covariant fashion. And so in this case, it turns out that it's the anti-ghost, and it's just the localization equations modulo some quadratic terms in B that you can actually integrate out because it's a Gaussian or an infinite dimensional Gaussian. And essentially, what you can show, well, the first thing that you really should analyze is, if you construct an action, you should see, like, are there any additional symmetries that we have now imposed? And it turns out that, or that we can find when we write the particular action. And it turns out that there is. It turns out there's a self-dual action that the auxiliary field satisfies. That is interesting for its own right, but I think what I want to actually emphasize here is that there's a natural gauge fixing that you can do on the action that actually preserves the Ricci conformal invariance. And when you do that, you can find out that you can kill all the components of the auxiliary field. You can kill all the components of the auxiliary field that have to do with the target space coordinate x. And so maybe I should actually, let me go back a little bit, because I think I need to introduce some notation. Sorry. These alpha Greek indices are going to run from 1 to 2. I forgot to mention that. So they're running from the coordinates on the world sheet sigma. And these I indices are going to run over the target space coordinates. So that's the capital X and the big theta, okay? So when I write this particular equation over here, what I'm really saying is I'm going to look at all the components that have to do with the target space X. And for the first world sheet coordinate and the second world sheet coordinate, all of those vanish. And so the only leftover components are actually going to be B big theta and B superscript small theta and subscript big theta. We're gonna set that equal to minus beta. The only reason I'm doing this in the slides is because if you go and read the paper, that's the notation that we've unfortunately chosen. So that's where that's coming from. But that's what it means. But the important thing is that consistent with this gauge symmetry that we found, we can actually add a quadratic term, and that's going to be this little b. So this little b, if you look carefully, that's the component of the field that is along the radial direction of the world sheet, but along the angular direction of the target space. You can add that term to the action. It's consistent with the symmetries, and when you integrate it out, and you relabel again the ghosts, so the only two remaining anti-ghosts that actually live is the one along the radial direction of the world sheet and along the angular part of the target space, and again over here along the angular part of the world sheet and the angular part of the target space. When you write all this out and you integrate it out, what you're going to end up seeing is that you can explicitly write the action in this particular form in equation 61. The main lesson here, ignoring all these calculations that I can give away through, if you email me, you want the slides, I can give it away if you want to look at it more carefully. But the key thing here is that now the bosonic part is actually minimized by precisely the tropical localization equations. You can check that explicitly by taking these limits, and you can actually see it over here, right? You can see that this was the original part that we had after we took the tropical limit, and the Cauchy-Riemann equation was deformed by this partial theta of x. All of these chi's and psi's, these are just ghost fields that make sure that we're ensuring the topological invariant. But this is what our action is. This is the thing that we would put in the exponential of that functional integral. And the only thing that we have to do is now, how do we evaluate it using this? And so it turns out that there's a standard.
Can you remind me what E was?
I'm sorry, which one?
E, the prefactor.
Oh, the
just a coupling
localization
constant.
equation. Oh, sorry, you meant this E.
There it was.
Yeah, sorry.
Yeah, okay.
But yeah, this sorry, I didn't find it. That 1 over E is something that we know as a coupling constant. It's just a real number parameter. It will matter eventually when we start to compute correlation functions. But for now, it's just a formal real number. Okay. Just so that everyone can keep track of where we're at the moment, let me just review this real quick. So I want you guys to remember is that this X and capital theta fields, these guys are just Grassmann even objects. Okay, so when you commute them, you're not going to get a minus, you're going to get a plus. But these chi's and psi's, they're going to actually end up being Grassmann odd. And so they're going to obtain a minus sign when you actually end up anti-commuting them. Okay, but continuing onwards, we want to actually compute the corresponding correlation functions. And it turns out that the interesting physical observables in the topological filter are precisely those that satisfy the BRST invariants. And of course, it's up to a BRST exact term. So you can always shift them. And so the way in which we can construct this is by looking at the natural space of geometric objects that we have. And in the target space, we actually have the Durand cohomology. And what we're going to do is we're going to actually map that to something that we call the BRST cohomology by taking any differential form in the target space of M and assigning it a operator on the space of fields. So remember, these psi's, those are Grassmann odd vector fields, but those are fields that we want to integrate over in the path integral. And so the components of this operator are going to be the components of the differential form in the target space. And so that's how you construct this guy. And if you look at it carefully, this is bigraded, right? It's not going to have any Durand degree because there's no differential form that comes along with it, but it's going to have ghost number degree P because each one of these ghost fields actually add one ghost degree. And that's going to matter when you try to figure out what are the correlation functions that are actually non-zero. It turns out that it's always going to be related to some sort of index theorem that tells you, oh, these guys are zero and these ones are not. Okay. And so, there's a very standard procedure. You can ask the question, if we want an observable, we have to make sure that observable is BRST closed. So we want to compute Q on any particular observable representative. And so if you do that, what you end up finding through a short calculation is that you actually get you get a new observable that has ghost degree P plus 1 when you do all the calculations. But its coefficients are going to come from the exterior derivative of W. And so what that implies is that if you want this thing to actually be an observable, in other words, if you want it to be BRST closed, then you must force that the forms that you're looking at in the target space cohomology, those guys must be exact. And so that's going to tell us which are the correct ones to construct. And in fact, you can construct a hierarchy of observables by taking exterior derivatives. And what you can do is you can very directly take the exterior derivative of this observable, and what you're going to find out is that it's always going to be the Q supercommutator of some new observable, then now it's going to have a ghost degree P minus 1, but the Durand degree is going to increase by 1. So these things are living on the world sheet sigma. And so what that means is that if we know that sigma is 2 real dimensional, these descent equations are going to eventually terminate once you go past the Durand degree 2. And so that's going to list out completely all the observables that we care about. And so we're going to look at the case where, to kind of finish off, we're going to look at the case where we are looking at the tropical limit of CP1. How do you actually compute that? And so, as we said earlier, we're going to view a tropical projective space as a foliated manifold that is diffeomorphic to CP1. And the real cohomology of TP1, you can actually find that it's actually spanned by the 0 form 1. That's not minus 1, sorry, it's just 1. And there's a 2 form that is just the target space coordinates dx wedge capital D theta. Now, you might say, where the hell did you get those things? What you can do is you can actually look at the cohomology of CP1. And if you apply the Maslov dequantization limit of the cohomology of CP1, then what you're going to end up finding is you're going to end up getting a distribution value 2 form. And this distribution value 2 form is then going to motivate what are the correct observables that we should look at in the tropical case. The other problem with it, though, is that in the tropical limit, the notion of finite dimensional integration measure, not the functional integration measure, but the finite dimensional one, that's also going to change. And it turns out that if we want to recover the correct instanton number to match the both sides, the original topological A model and the tropological sig model, then you kind of have to change the notion of finite dimensional integration to actually use the tropical notion of integration. And it turns out that taking limits and so forth, the natural notion of tropical integration is just to take the max of that function. And so we keep the angular coordinate to be regular finite dimensional integration. You can use the Lebesgue measure, but the integration measure along the radial x coordinate, that's going to be tropical. And when you compute that, you're going to get precisely 1. When you pull this back to the world sheet, then you're going to get precisely the instanton number k that we actually want. Okay, so doing that, this was the key point that I was saying. You can try to compute these observables. You can go through the standard arguments that actually occur in the relativistic case, and you can actually directly compute this. Unfortunately, I'm not going to go through all the details of this because I would have to count instantons and anti-instantons. But the point is that you can actually compute this, and what you find is that there's a selection rule that when you have n punctures, and that n punctures is equal to twice the instanton number, you're going to get 0. But when it's an odd number of instanton numbers, then you're actually getting a finite result. And it turns out that this result, to compute these correlation functions, you can actually do it on a generic genus 0 Riemann surface. To extend it to non-zero genus, we actually need an additional argument. But roughly, it does go like this. Essentially, what you can do is, if you actually have these k punctures, so you're going to insert observables at P1 through Pk, then you can actually use our symmetries to actually map k of them to minus infinity, and you can use the same gauge symmetries that we found in our theory to map the other k to infinity. And so there's only a single left out point at 0 that's actually going to be an issue. And when you go through the whole calculation, you reduce it down to this single observable that only has k instanton number, then that's how you end up getting the result in the previous page. But like I said, the details are in the paper. I have to speed up just a little bit so I can make sure that I get to the whole thing. Sorry, it's a long presentation. Another important thing, though, is that you can actually construct handle operators like in the usual case that increase the genus by 1. In the case of the topological sigma models, if you want to actually insert a handle operator, what you can do is you can run through the arguments, and you can find out that if you actually want the foliation to close, the winding number actually has to be 0. But the important thing about that is that it tells us that if you want to construct a handle operator for these topological sigma models, if the winding number is 0, then you actually can map this handle operator to a single point. So that means that we actually have a local operator, and there's only 2 candidates for that local operator. We either have the local operator that's generated by the cohomology class 1 of the target space, or the symplectic form of the target space. And so you run through it, and you actually find out that it's twice the observable that you can construct by using the target space on symplectic form after it's been tropicalized. And what you can do is now you can actually compute the partition function. So that's the original, that's the whole functional integral over the topological sigma model to all orders, so all loop orders. So what do I mean by loop orders? I mean like a sum over all different genuses, and we weigh it by this GS, which we call the string coupling. So it's a little confusing, but this is terminal. This is just notation from the standard topological sigma model, where we weigh it by G string, and it's 2G minus 2. Some of you may recognize this as being minus the Euler characteristic. But the important thing is that now you can decompose this correlation function into a sum over different genuses. And this guy right here is a one punctured, a single observable at a single point, but it's evaluated at a Riemann surface of genus G. But if you want to build that Riemann surface, the foliated Riemann surface of genus G, what you can do is you can actually relate it back down to the Riemann surface of genus 0, which we have the answer for, right? That was the lambda 2k plus 1, but you have to insert g minus 1 many of these Hanel operators. And so you can go through that calculation, and when you go through the whole calculation, you actually end up recovering precisely the exact same thing that you would get before you took the tropical limit. So that's the main result for this paper. The main result is that if you take the tropical limit in this particular way, then you're going to see that there's a refinement of all the standard arguments that we have for the usual topological sigma model. And after you take the tropical limit, then you're going to see that when you actually get all those, you go through all those refinements, you can get the exact same answer. And so what that's suggesting is if you take the tropical limit of the path integral, of the functional integral in this particular way, you're going to get exactly the matching. And that's precisely what Mikhalkin's theorem was saying. It was saying if you want to compute the Gromov-Witten invariants, you can compute the same Gromov-Witten invariants by taking the tropical limit of them by using methods of algebraic geometry and all those sort of combinatorial techniques. Over here, what we're doing is we're doing it at the level of the functional integral, and it turns out that it gives us precisely the correct matching. And so that's what the you have a question?
I was going to ask. So here, the target space is smooth, right? And so CP1, there's a very natural singular space one could also ask about. It's like versus teardrop, or just put a weight in one of the projected coordinates. Do you know, or can you do your computation for such local orbifolds too?
I don't think we've tried for, well, one second. When we take the tropical limit of CP1, what we're going to end up getting is an interval, right? Because you get those fixed points. And I think when we go through the details of the paper, we have to deal with those singular points, and that was this whole argument that we said that we dealt with them by extending the coordinate systems. So over here, when we got these balancing conditions, this is going to tell us how to deal with those orbifold points. We didn't consider any complicated orbifold. That's the other thing. So we've only done it for very simple things. I'm not sure. Does that answer your question roughly?
I guess so. But when you say you deal with the orbifold points, what do you mean? Because, like, for example, the teardrop I was thinking of just locally has a patch where it looks like C mod some finite group Cn. And I'm wondering if the computation you're doing here is sensitive to this thing, which is topologically it's still like a sphere, but it has this one point that locally looks like an orbifold patch, or if this is something
I
that
don't think we've
the
actually.
computation
Yeah,
is not
I don't think.
sensitive to. Because Gromov-Witten invariants have been studied also like in the setting of orbifolds, of course, and I was just curious how close you get to that.
I don't think we've actually explored it in that particular context, but I would imagine that, if you have the sort of orbifold structure and you say I'm going to mod out by say Z4 in the simplest case, so just an abelian group, then I believe that you're actually going to end up recovering like this particular calculation, because near like the neighborhood of that singularity, I think when you go and do it carefully, it is going to be like C4. Sorry, not C4. It's going to be C mod Z4. So the complex numbers mod the integers 4. And if you want different singularities, and there are different singularities that are allowed that we talk about in the paper, you would mod it by different groups, so you would get like Z3. The question though is, what are the sort of admissible singularities that you are actually allowed? And I think that's going to that question that you just asked, like what sort of orbifolds can you actually consider? And I think when we were doing the calculations, we only found that you have to consider Z3 and Z4 at most, and that generates all of them, at least on the world sheet. And this particular example, I do not know what happens if you have, for example, the acyclic group or something more complicated. And it's not something that we had considered from the physics side, because the only reason why we're considering these orbifolds is because they should be coming from the gluing conditions, right? Like where these junction points meet up. So I think that's to the level that we've understood it at the moment.
Okay, thanks.
Okay, so let's finish up since we have only a few minutes left. So I just want to mention that we do have a few further results. So to connect to the original thing, we said originally the reason why we were studying this is because we want to extend string theory to this sort of non-equilibrium string theory where we had a triple decomposition. So the topological sigma model shows that we can explicitly construct this wedge region. And the interesting thing is that if you try to analytically continue this, so we actually have a real-time theory, so it's no longer Euclidean. Then what you end up finding is that you no longer get, for example, the Virasoro algebra that you actually see from regular relativistic string theory, but you actually recover the BMS3 algebra. And the interesting thing about this is that this algebra has actually appeared in different contexts when people are taking non-relativistic limits of string theory. People have seen it in like Einstein-Cartan. Yeah, exactly. Newton-Cartan theory. I think there's this whole literature of like Carolian string theory and all sorts of other non-relativistic strings. People have also been studying in the concept of flat space holography. So it sort of seems as though it's formally reaching in that direction. And that kind of makes sense, because if you go back to the very beginning of these slides, when we had the Stern-Kellish formalism, you're supposed to evolve it to this turnaround point. And that turnaround point, you can generically, from the physics side, send to infinity. So it is actually probing some sort of infinite distance in the target space. So it kind of makes a little bit of intuitive sense that we're actually getting these sort of asymptotic symmetries. What we also found is that you can consider these topological sigma models when we actually have a boundary condition on the target space. And we know historically when you did that in string theory, you actually found this notion of Dirichlet branes. And so we were actually able to repeat the same arguments. It's a very short calculation, and you do find the notion of tropical branes. It turns out that it comes with this new boundary conformal algebra that we actually wrote right here, and you can look up in this paper. And it turns out that interesting thing when you actually canonically quantize these open string states in this tropical limit is that you actually get an infinite number of free particles that have increasing mass. And if you're a string theorist, then you would actually be like, oh wow, that's actually interesting, because if you were going to look at the asymptotic limit of any sort of string amplitude, you know that's precisely when the string Ricci's decouple. And so they have to become free particles with an increasing number of mass, because you have all the different levels that string theory produces. So it seems to be consistent from that. There was a few mathematicians, and I guess there's a few mathematicians whose names I put it in the reference. They've actually began studying this algebra because they were looking at it in the context of Carolian physics. So, the question of like, can you actually construct a conformal field theory, operator product expansions of all these observables that we constructed for the topological sigma models? Like, what can you get out of it? That would be a good starting point if you want to investigate this from a more mathematical point of view. The other thing that I realized that I wouldn't have actually been able to get on this particular talk is that there is a natural notion to couple this to tropicalized topological gravity that we call tropological gravity. The natural question is, if now you've managed to figure out what the theory looks like when you have these sort of fixed Jordan structures, so fixed foliations, what happens when you allow the foliations to now be dynamical? What sort of new singularities are going to end up forming? And it turns out that the main thing is that you actually just have to replace the kinematics of the Jordan structure with Einbein's and the connection that's invariant under Galilean kinematic symmetries. And so this is something that we're going to release in some time. Most of the results was actually already done a few years ago, but we just didn't have time to write it up. But the interesting thing is that this actually has a very direct, explicit connection to Novikov-Morse theory. And we can kind of write it as a Ricci Flow like theory, but we're just gonna keep it there for now. It's a little vague because I only have 30 seconds. But there's very many natural directions, but just to kind of make sure that I'm not killing any more people because that was really fast. I've been happy to answer questions for the last 30 seconds. So yeah, thank you again, and I'll be here for as long as you want.
Thank you very much. I guess applause in some way or another. Maybe I'll start directly with a question. So the last Novikov comment that you mentioned. I know Novikov most theory, I guess, in this sense, where instead of deforming the exterior derivative with a function and shifting it by d of that function, you just have some one form. So in this case, what's like the natural one form that appears in the construction?
The natural one form is actually coming from this Einbein. So that is something that is not explicit from literally just telling you what's the new field content, but what you're going to end up finding roughly is that the Einbein is going to, when you actually look at all the localization equations and you apply all the gauge symmetries to be found from the topological sigma model, what you'll find out is that in some local patches, this Einbein is actually precisely the derivative of some additional function. And that additional function is going to actually tell you the direction of the foliation. So it's some sort of circle valued Morse function.
But it's just like locally exact.
Yeah, it's
Location.
locally when you first do the calculation. Can we extend it globally? I do not remember at the moment. I do not remember. Yeah.
And how does it relate to Ricci Flow? You can sketch that a bit.
Okay, so that one is, it's a little bit more complicated. That really just comes again from looking at what the localization equations are. And if you again go through, use all our symmetries and you gauge and you gauge fix it in the proper way, then what you're going to actually end up finding is that it actually reduces down to, well, Ricci flow like flow equations. That's only after the addition of a certain particular potential. But like I said, this will be revealed once we actually get to the paper. Presumably we will be writing it up in a few months. I think this was probably the original reason why perhaps this didn't catch on yet. I think this is actually the reason, the interesting part. But like I said, I can't say too much because I think my advisor might be like, you shouldn't reveal it.
Okay, no worries, no worries. Don't make yourself problems. Do you have any other questions? I think we do not. Thank you very much for this very nice talk. Let's thank Andrés again.
Thank you, everybody. Thanks for the invite.
And then we're done. So there'll be a seminar in person again next week, and hopefully see you around, Andrés and Emil. Thank you for the very nice talk.
Yeah, thank you, appreciate it. Have a good one.
Thank you.
Happy
Bye.
Thanksgiving.
Bye bye.
Thank you.
Thank you. Bye.